So welcome back, everybody. I'm Melvin Davis, and I'm chairing this afternoon's session. So welcome back. And our first speaker up then is Johan Frid, who's going to present the work of Thread 3, Discovery from the Written Word. Thank you.
Yes, so I'm Johan Frid from the Lund University Humanities Lab, and I'm running Thread 3 together with Jonas Björk from Epidemiology and Mattias Olsson from Theoretical Physics and Astronomy. And we are not having a lot of videos and stuff like that, but we are doing a lot of text instead. So, talk will be first very short introduction, then I will talk about something called topic modeling, go into how you can do that and what it is. And an extension of that is how you can use semantic lexicon, semantic meaning lexicon to augment these topic models. And then I will talk a bit about information extraction, a study that we are doing on analyzing abstracts from papers, medical papers mainly. But let's start with saying something about what this is. I mean, this is language technology. I mean, how you deal a lot with language. And this is a good summary, I think, of progress in different, what kind of different fields there are and how far we are in different. So you can see that mostly solved, for instance, spam detection, that works quite well. Something called part of speech tagging, saying which word class a word has. And named entity recognition is of fields that are considered solved. The field we are working is basically this one, I think, information extraction from papers. But you can see that there are lots of work to, I mean, there are lots of different subfields in this language technology, which is a bigger field. And of the hard ones, there are still some, I mean, question answering and paraphrase detection. That's kind of difficult grammatical issues that you have solved there. To some extent, we are moving into this with the work we are doing here is also to some extent in this area, because what we are trying to do, one thing we are trying to do is to summarize the papers in some ways. So just to get you a view of what we are doing and where we are in this bigger language technology field. Some things about what discovery of the written word can be. One thing that is quite common is to, well, use this one instead. So, given that I know something, how can I find out more about this thing? So, given the information I need, I know I can have I know these papers but I want more of the same, so to say. That's something you can find out. And then there is regular text mining, what is actually in documents, what's in the text, what can we learn about the text, what can we extract, what kind of metadata can we get out of it. And then there is an issue, something emerging here, something called distant reading, that understanding literature may not be more by studying particular texts, but by aggregating and analyzing massive amounts of data. I mean, I'm not presenting any numbers here, but you probably know that online archives like Archive, PubMed, other stuff like that, I mean, that grows enormously, and trying to keep up with all these enormous amounts of text that is being, journal papers that is being produced, can be quite difficult in any field, I think. And then there is the aspect of machine reading, that the machine can actually read for you and actually converting it to some kind of interpretable structured knowledge that humans can use. So that's sort of, I mean, it's a selected thing. I mean, there are lots of other things you can talk about when you do discovery from the written word. But I'm going to specifically talk about something called topic modeling here, which is a form of unsupervised learning. I mean, within language technology, we use lots of machine learning, and many use perhaps supervised learning method, but this particular method is unsupervised learning. So the idea here is that you have lots of, I mean, if you have an archive like this, and you know that perhaps there are different topics in there. And so the idea is to probe into the texts and try to find the underlying structures and trying to find it by finding recurrent patterns in the literature. It's sometimes said that this is sort of an exploratory way of doing it, so it needs some kind of human interaction when you do it. But basically, you try to group documents that use similar words and words that occur in documents that are similar. There are methods for these: latent Dirichlet allocation and non-negative matrix factorization, which is the one I have used the most. So the idea here is to have a corpus, as we say, and a corpus for this talk. Is basically a collection of texts. It's lots of text. So it's a body, could be like 1,000 documents or something like that. A corpus. That's a sort of common phrase used in linguistics and computational linguistics. So corpus of unstructured text documents. It could be news articles. It could be tweets, transcriptions of speeches, and it could also be journal papers. So you don't normally have any annotation or training set here. And the output here is then to find out what are these papers about? What topics are the papers about? And what you get is actually sort of descriptors in the form of the words that are most salient in each topic. And you can also get associations between the documents and the topics. This is being used in several places. For instance, recommendation systems use this kind of technology. It uses, clustering, separating. If you have a large text corpora, you can cluster it in different ways. And it's very popular to use in things like media monitoring. People who follow Twitter feeds, so they can instantly discover when something new happens. It's very popular, for instance, in political science, things like that, where they try to monitor what happens, what is the hot topic that is being discussed right now. It has also had use in things like, warning systems like, Twitter feeds, for instance. You can very quickly discover things like, if there is Ebola outbreak is a good example, for instance. When there was an Ebola outbreak, it was out on Twitter a lot earlier than the WHW could get out there, for instance. And somehow, if you could use some kind of text analysis to leverage that, it could be helpful in that way too. But that's a far application of it, perhaps. So what we use here is something called the vector space model of text. So the basic idea is here that you have, in each text, you have some kind of keywords, you have some kind of important words, and these keywords describe the topical content of the documents. So each document is somehow characterized by one or more words that are being used more than other words. And then the vector space model says that in a corpus, again, each unique word in the corpus is then one dimension. And each document is a vector with a non-zero weight for each word in that document, but with 0 weight for the other words. So the words, in some sense, become the features that we use. And this is perhaps more illustrative, that we can represent documents as vectors. So here we have the documents, A, B, C, D, E, and F. And then we have words that somehow occur. So probably these documents are probably astronomy related, because then here we have weights. We have words like nova, galaxy, heat, etc. And probably B and C might be related to that as well. But then you have D, E, F. Here you have more words like film, rule, diet appears there suddenly. But the idea here is that you can build a sort of vector representation from all the words in a corpus that relates the documents and the words in a matrix like this. So normally you start with the raw frequency terms. You just count the words in each document, and then you can apply some kind of weighting or apply some transformation to do it better wise. You can relate it to the maximum now the most frequent word, the frequency of that word, for instance, or you can do other stuff with that. But the starting point is always the raw term frequency. And another way of looking at it is if you have, for instance, here you have 4 plays by Shakespeare, and you have then counted all the words in there, and you have found then words like battle, soldier, fool, or clown. And here you can see that the 2 documents are similar if their vectors are similar. So in this sense, these 2 plays are more similar to each other than these 2 plays because they have vectors that are more similar to each other. The frequency profiles are more similar to each other than the other ones. And the same goes for the words. So you can have also, the words also have vectors, so to say. So in this sense, we can both determine that these 2 plays are more similar to each other, but we can also detect somehow that these 2 words are somehow related because they have similar vectors. And also battle and soldier, of course, you could also relate that these 2 words would be more similar to each other than the other 2 because they have similar vectors. So that's the basis of this kind of work, the term document matrix. And now if we extend it, because it's 4 words, 4 plays, let's do a little larger examples. Here we have like 25 or 20 documents, I think, 20 words. And now you can see here that each column here is a document. It's named by the D and the number. And then you have the words in here, and they are sorted. They appear alphabetically here. And and then the idea is that the darker a cell is here, the higher the frequency is. So here, for instance, in this document 17, the word launch is very frequent. It occurs a lot in that document. And the reason I want to play this, this is the only animation I have. We have had lots of them before, because this is quite illustrative of what's happening. So this is the same picture, but now it's an animation. You will see what we are doing with this as it plays. It started, and you can see that now you shift all the documents to each other, and then you also shift the words to each other. And well, now you probably see that there appeared some clustering of the words and the documents. So somehow we rearranged the rows and the columns in this matrix, and then there appeared some kind of larger collections here and look, we now actually have words that are similar to each other, or somehow we should air, pollution, power, environmental. I mean, that are all words that, I mean, according to our intuition, they seem similar at least. Illegal immigration, amnesty, aliens, also quite similar. Shuttle, space, launch, booster, also similar in that sense. So we have kind of achieved a grouping here of words that are similar in topic style. And we also have a grouping here. We don't know what the documents are, but there probably could be some kind of labels on these. But now we know, for instance, that document 0, 14, 15, and 8, they probably form a group. So now we have sort of achieved a grouping of both the words and the documents. So, I mean, and that's the basis of this topic modeling. We just I'm saying it's not that easy to do it. But so basically we start with this term document matrix, and then we rearrange rows and columns which can then represent words and documents to form these kind of clusters. And now suddenly we have these topics that we sort of can infer from there. And I'm going to illustrate that by, that's one thing that I've learned from being in this data theme, that it's quite good to work with sort of simulated data, that you can sort of, you don't always have to use real world data to illustrate something, but you can use simulated data. And one way I can do this is to use Wikipedia. So let's say I of course download Wikipedia and convert it to text. That's easy peasy. And then we find articles that contain some word that we can change. So we can have maths, physics, culture. So we extract all articles that contain an instance of a particular word. Then we apply some text processing to that, remove common words, downcasing, etc., which are quite good to do. And now the words in those articles will be features that can be related then to this word X. And I'm using a technique here, I mean the non-negative matrix, it actually should be NFM there, or NMF. So I'm using a package that actually does this NMF thing for me. So I did this first for, now this is in Swedish, so it's the word kultur we have here, and I found 16,000 Wikipedia articles that contained this. And we can see, and then I did this term document transformation and then the matrix factorization. And this is what came out. So you can see that there appears to be related words here. So you have language, human, university, religion, culture. That's not the best one. But then here we have author, book, novel, and write, literature, etc. TV, series, program, episode, channel, etc. We have art, artist, exhibition, painting, etc. So this has come out automatically from this topic modeling analysis. And you can try to, find some labels for these topics in some ways. So we have different kind of art manifestations here, building related stuff here. You have museum related stuff, church related, and then art related. And then we have topics that are related to different media things, but they have actually fallen in different topics here. So we have film related in one, author, TV, music is up here, newspapers, theaters, etc. And then there are others for people, society-like things. And there is one here related to politics, so it's probably, culture, politics in some sense. I did a similar one for physics, or physique. And, I'm just giving you my interpretation here. So you can see that there are a few that fall out here. We have education-related stuff. So we have school. So, that physics is something that is being used in education. So we have school, education, pupil. And here we have technical, high school, physics, civil, engineer, royal. So that's my type to do. And we have a nice one here. We have the Nobel Prize category here for related to physics, which is, so we have prize, Nobel Prize, physics, discovery, etc. Sometimes we have, it's not perfect always. We get topics like this that you can't really make anything out of it. And here you can see, it's not always related to physics as a subject, but it could also be related to the physical game. Like a body, that's like ice hockey, for instance, is a physical game. So you get all these ambiguities that words actually have, so that kind of goes in. I kind of couldn't resist doing it for data, of course. So, and so let's see what we find here. Well, we actually get astronomy as a subject here, which is good. So we have planet, Earth, star, etc. We have university, so university people use data a lot, don't we? So we have university, library, Swedish, research. We have language-related things here. Letter, language, well, this is sort of, alphabet is there as well. There are some computing terms there. But we also have this rune, inscription, runestone, carving, etc. And then we have lots of computing related here, like internet network, blah, blah. So gaming is, of course, in there, data gaming, and program related stuff here. But you can see that there are some things. Then we have this one, which is sort of biology related. So we have art, female, family, etc. And here we have something that is related to. So for data 2, perhaps we should have people from biology and political science, something like that. I don't know. We don't have VR here, which is kind of sad. We have, virtual reality. We have film, TV, etc. But that probably has to do with that. This is Swedish Wikipedia, and they probably haven't used that expression, virtual reality, as much as you might have, you could have. So, some remarks then about this topic modeling thing. It's kind of, this is something that needs to be interpreted in some way. It's kind of hard to quantify. Setting this up in a machine learning like you normally do with training and testing sets it's sort of difficult because it's so likely to give a bit of different results. Another thing I didn't tell you, I just showed it, that you sort of need to choose the number of topics. Maybe you saw that there were different numbers. In data there were 12, in the others there was 16 in different. But that's something that you have to tune in some way. There are ways to determine that by machine, but the problem is that it's not always that then when you show the best number of topics that you have found, when you show that to a human, it's not always that they agree, actually. So even though there may be computational methods to actually measure which number of topics should be the best, it's not always the case that it's the work. Another thing is that the topics are not really self-labeled. What you get is basically a bunch of words that somehow are grouped together, and then it's up to you as a researcher to label it in some way. So there are some tricky things here. Still, I think you can get a good peek with this into unstructured data in some things. You can actually see things falling out. And what I didn't show you, that you can actually get a similar list with the different documents. If you have labeled documents, you can actually get a similar list for each topic that goes into each, so to say. A nice thing is that it's also sort of language independent. You can actually use this for any language, Swedish, English, German, or maybe some of Nicole's languages, if you have enough text. But this leads me to the next thing here, because now we can try to do something here that's called semantic tagging. This is another then approach to analyze meaning in text documents, and it's quite a simple approach actually. It's difficult to create this kind of lexicon, but you can use a semantic lexicon, which basically is a list of words and then some kind of semantic category, semantic meaning-wise then. And the way you work with this is that you can tag each word in a document with a semantic tag, and then you can simply list the tags and their frequencies. So you get a descriptor in some sense for the document. And you can actually work with this in vector space as well. So instead of Word document matrix, you can use a semantic tag document matrix, and then you can do basically the same thing. So we have used a system that is, we have cooperated with people in Lancaster. They have developed this semantic analysis system. So they have categorized different. This is actually based on, I think it's Longman's dictionary from some year, I don't know. So they have basically determined that there are some kind of top categories here, and then they have just given each category some kind of letters, and that's just a label. It's just a shorthand. So you have, in A, you have general and abstract terms. In F, you have food and farming. K for entertainment, sports, etc. So that's their kind of grouping that they have made. Trying to put everything into a box here. And then there are more fine-grained levels within each of these categories. You see, category X here was psychological actions, states, processes. And then there is a more fine-grained division in this. So you can then split up this super topic in different subtopics. And then each word in the lexicon sort of gets a label. I think there is it? Yeah. In this one, you can actually see how it works. So let's start down here. Here we have basically just a list of different words, and then you have the tags that are associated with each word here. And what we have done is that we have translated this into Swedish using this one. This is a publicly available Swedish-English lexicon. It actually works both ways. So we have both the Swedish and the English version. So the thing is to just look up the words in a document and then tag them with this code, sort of, which is basically just a shorthand. As you see, I mean, there is the code, and then there's a descriptive label for each of them. So, well, this is maybe, yeah, well, so you tag each word, and then you just count, sort of. I mean, you can do it more sophisticated, but as a start, it's very easy to just count what is happening here. So, and then we have the difference of grammatical, names, modified change. So you just make a list of your tags in this way. And let's see if this is visible. Yeah, here is an example. Let's see if I can, I didn't really prepare this, but let's see. Sorry for this. Yeah. So it says welcome, and then here I'm just going to put some random article. What it does is that it takes the Wikipedia article on some topic, and here it became Turning Torso, which is the building in, okay. It splits the page in here. And there you can see, okay, so that's kind of similar to the pyramids that we had in the future. So the best label, so the article for about Turning Torso, 3 minutes, so yeah, that's fine. The article for Turning Torso contains then lots of words that are related to architecture, house, and buildings. And then there is some noise here as well, but I mean, written communication, well, that's kind of weird. But you can see that the top category at least gets it gets that right. Let's try one more just to, well, I took the same. Darkness, okay, that's, yeah, okay. So there is actually there is a category. That's very nice, very convenient. It's, so it works. It's a meter. Well, let's see what it Okay, affect, modify, change. Yeah, well, sort of. But then actually measurement distance gets very high in here. Measurement, well, general. Measurement, length, height, width. So the Wikipedia article, again, for meter, contains these terms that you use. So it's kind of a semantic labeling that we can get. Let's see, where is my... No, sorry, that's Monica's. I lost my... no. There we go. So what you can do, I'm doing this quickly. What you can do now is that you can compare two different. So for instance, if you want to compare turning torso and meter, sort of. So you can take, well, not those two exactly, but you can take two corpora and you can then tag the words semantically. And then you count the tag frequencies in C1 and C2, and then you compare the frequencies that you have. And then you can use some kind of, well, a good measurement here is it's described in this article by Rayson. A good measurement for comparing frequencies in different corpora is the log likelihood ratio. And then you can, depending on what you get out, you can sort the tags on this log likelihood, and that will give you a list of semantic tags that are overrepresented. So again, here I have compared kultur and physique, taken the Wikipedia articles from each of them, and again, this is Swedish. So what comes out here is that for kultur, we get the tags for, I mean, that means that there are lots of words in here that are associated with places, and you can actually see some of the words that occur together with kultur then. So city, area, population, etc. And then here we have, capital, nation, etc. And then again, architecture, like museum. So these are all related to culture. And then for physics, you get things like science, ability, measurements, etc. So and words like energy, chemistry, science, electron, field, and things like that. So using this, we can compare different corpora and find out what semantically comes. I did a small test, but I'm going to skip that because of time. So because I want to summarize this. So what you can do with this is you can label documents semantically. And we can compare collections of documents and find out in what semantic ways they are different. We can also somehow, that's the one I skipped, but we can somehow quantify the relative distance between terms. What you can do with this then is that you somehow can curate literature banks with this. When you have lots of literature that you want to know something about, then you can get some kind of semantic analysis of it. Again, monitor and detect changes in media streams. And I think a nice thing here is that you can actually combine this with the topic models, because we can now apply these semantic taggings on the words that we get out of the topic model. The semantic lexicon on itself, it's quite hard to produce. I mean, somebody has to sit and actually determine everything here. So one idea we have for the future is to do this automatically. So we can induce lexicons, for instance, by comparing the text of a Wikipedia article with the category that is in a Wikipedia article. So if we can relate that in some way, we should be able to produce some kind of, automatically produce a version of this lexicon. So that's where I finish, I think.
Thank you, Johan. Comments, questions, or thoughts? And please, again, wait for the microphone so we can hear your questions later in the recording. Thank you. Please.
Just one comment, I suppose, where you had the question mark on the physics. Yep. It looked a lot like it was popular science, actually, which I think is pretty cool that you managed to dig that out.
It could be, yeah. Sometimes you get the full category with just English words instead of Swedish, because there are lots of English words in the Wikipedia. So sometimes that falls out as a topic on its own, and that's. I mean, it's nice that it detects it, but in some sense it's also noise. But it's good that you.
Okay, we'll go for Brian first, please.
I have a question. Have you thought about maybe including newspaper articles and looking at the time dependence? I mean, if you, for example, take your first 4 words you had with the battle and soldier and fool and clown, there might be a temporal dependency in its relation to, for instance, American president.
That's a very nice, very nice idea actually. You could do that. I mean, people have studied word usage over time. So, for instance, looking at words like war and peace and comparing that over time. And of course, you find lots of, in 1914, you find lots of war words, and in 1918, you find lots of peace words. And so the problem there is to find enough historical data, because these old newspapers are, I mean, they are about to be scanned and OCR'd right now. So, but I think that's a data source that is going to grow, and we can find interesting things there. You can also compare things like telephone and telegraph, for instance. You can see that in the 19th century, it's a big change where that happened. And probably you can do something similar for modern text, like telefax. I mean, nobody uses that anymore, but it probably peaked in usage somewhere around the 80s or something like that. So there are, I mean, people have worked with that kind of historically looking at word usages like that.
Okay, question from the front, please.
Thank you. I think it's a great demonstration how you can use data science and hierarchical clustering to classify, to cluster documents. I wonder, when you do this type of clustering, it all depends on the distance, similarity, how you define similarity between your documents. And the similarity distance metric depends on the data.
Yeah.
So I wonder, how do you define similarity for texts?
It's frequency based, basically. But as I think I may have skipped that quite quickly. But you start with the raw frequencies in a text, but then you can somehow make transformations of it. So you can always relate it to the maximum frequency or the word that is most frequent, or you can take some kind of mean frequency. So you can do transformations to all these things. But it's basically frequency based. It's not like and that's kind of stupid in a way, because you don't really know that these words should be together. So you just measure the similarity based on how often they co-occur. That's
robust.
Yeah.
Thank you.
Thank you. One last question at the back then, please. Just wait for the microphone, please.
So technically, how is the exchange in rows and columns done in order to get that diagonally blocked matrix? Is it uniquely done?
You mean if you can get to different... I think there are different techniques. I think there is a way of... I'm not an expert in this matrix. I mean, I know how to apply it. I'm not. I think there actually is. It is possible to get an exact solution, but it's usually you use an approximation to it, and then I think it's possible to end up in different. That you actually can get different results from it, and that's what you usually use, because it would take too much time otherwise. But I think you get sort of similar results, and I mean, it's not totally different anyway. So, but you might get small changes in the actual things here.
Okay, let's thank Johan one more time, please.